In this video, we're going to talk about the equilibrium constant Kp and the exam style questions. So here you have a Haber process, and the Haber process, you've been given the partial pressures of H2 and N2. Also the total pressure of 10 megapascals. Now this is a different unit to what you normally have, so basically they create the unit for Kp from those units. So it's Kp megapascals to the -2. Now you have to work out the value of Kp and an appropriate number of significant figures, but you don't have the partial pressure of the NH3. So let's show you how you do it. So if you can do this already, just do it. Okay, but if we go here, we can just say that here is the equation. So straight away we've got the equation NH3 squared and then N2 plus H2 cubed, and you got that from the balancing of the equation. The 3 comes from the H and the 2 comes from the NH3. Okay, and then what we can do is we can say N2 and the partial pressure of N2. So the partial pressure of N2 is in the question, and you can see it's 1.75. Now, if it's 1.75, you also know that the partial pressure of the H2 is going to be there as well, and it's 1.5. Now, we don't know the partial pressure of the NH3, but we know that the total from the question, we can look over here and we can see that it's 10. So that's 10 megapascals is the total. So all we have to do is say, well, if the total must be all 3 of them added together. So we add this to this, and then we take it away from 10. And if you take it away from 10, you get 6.75. So we've got our partial pressures now just by noting that the total pressure is equal to the partial pressures added up. Now, from that point, we can then look at the equation here, and we can just copy out our numbers. So we know that NH3, for example, is 6.75 as the partial pressure. So 6.75, okay, and we'll put in the units. But that, according to this equation, is squared. Okay, and then we draw a nice line. Then the N2 is 1.75. Okay, and then that, again, megapascals. Okay, and that is times by, if you look here, H2 cubed. So H2 is 1.5. So we go 1.5, but this is going to be cubed, and that's going to be megapascals again. Okay. So I'll put the megapascals just in for this reason, just a quick practice of units. So you can see here that the megapascals, there's 2 of them here, so they cancel. Okay, and that means you'll cancel out 2 of those. So that means there's 1 megapascal and 1 megapascal here, which means 2 megapascals, and then times it by -1 to bring it up, and that's why you get megapascals to the -2. Now if you put this into the equation, okay, you can see that the answer is 7.7142. Okay, so 7.7142. But the question says give to an appropriate number of significant figures. You can see with all of these, this is a nice one because all of them have 3 significant figures. Something to really note is that if you've got 3 significant figures and the last one is a 0, so if the last one is a 0, it's still a significant figure. And it's 0, and that's because that 0 could be as a result of 1.501, 2, 3, 4. So it's still significant because the number after it isn't necessarily 0. It could be 1, 2, 3, or 4. So we've got 3 significant figures. So our final answer is going to be 7.71 megapascals to the -2. And that is one of your simplest questions to do with just using the total pressure to work out Kp when you're only given some of the partial pressures. In this question, again, we've got the Haber process, but we have got the chemists mixing together 0.6 and 0.9 in a sealed container. So it's in a sealed container, which means that we can then get a total pressure down here, which is 200 kilopascals. And it's giving you the equilibrium pressure of one of the components, but not giving you the equilibrium of the others. It's just giving you the initial. Got to calculate Kp, show what you're working, and include your units. So let's put that to the side. And if you look here, we're setting up our ICE tables. So ICE tables, initial change and equilibrium. So change is basically whatever is used up. So we know from here, so we go over here, we've got 0.6 and 0.9. So that's 0.6 of N2 and 0.9 of H2. We know at the start we have nothing of the product because it hasn't reacted yet. So the change is the amount that's been used up. So if we have 0.35 remaining, which is from the question, it says 0.35 there. What is the difference between these two numbers? That's the amount of N2 that's been used up, essentially, because we're all talking about moles here. So this is all moles from the question. So the difference is 0.25. Now we use the balancing in the chemical equation. So if I've used up 0.25, because of the ratio of 1 to 3 here, okay, if we times 0.25 by 3, that will tell us how much we've used up of the H2. Now, if that is the case, we can then go, right, well, how much NH3 have we actually made? Because if we've used up this and we've used up this, how much would we make? So we can go from the balancing again and go N2 to 2NH3 is like timesing by 2. So we take 0.25 and we times it by 2 and we get 0.5. Now the important thing here is that the change, what you have used up essentially, okay, that's what you've used up. That's what you started with. So the difference between here and here is going to be how much remains, and that's going to be how much at equilibrium. So we've got 0.15, difference between 0.9 and 0.75. Now, this change is from 0 to 0.5. This is how much you've made. So that is your equilibrium amount. And you can use these ICE tables all the time to do this, and I practice it a lot. Very, very common in the exam. Okay, so we take that down. And then we start to do our mole fraction, because remember, doing the mole fraction first, then the partial pressures. So I'll show you one of these mole fractions. So 0.35 divided by 1. So if I got the 1 because I added all of it up together. So if that is the case, we start off with that, but this is what we ended up with here. So we're not adding these together, we're adding these together down here. So 0.35 plus 0.15 plus 0.5 is 1, because that's the total number of moles. And then we've got our number of moles that we've got, which is 0.35, okay, and we divide it by 1. And that ends up with 0.35. We did the same here, so 0.15 and 0.5. You can see it's all divided by 1, so it's the same number. Partial pressures is done by taking the mole fraction and timesing it by the total pressure. So the total pressure is 200, so we take this number and we times by 200, and we get 70, and we take that number, okay, and we do the same and get this number, and we get that number. Okay, so this 30 here is just literally going 0.15 times 200, and this 100 is 0.5 times 200. So I'm showing you one example calculation and the rest showing you through. Now, if that's the case, we need to do the actual expression. So we did it from the last question, so I'll put it in. You've got your expression here, and all you have to do is put the numbers in that you've got for your partial pressures. So if we put the numbers in for the partial pressures, we can see that, and we come up with 5.29 times 10 to the minus 3. Now, if it's 5.29 times 10 to the minus 3, we still have to do the units. So if I take this over here and I start just doing the units, you can see up here, this time we've got, in here, we've got units of kPa. So basically that means that we've got kPa, remember that is squared, and then we do N2 here, which is kPa, and then another kPa, which is here, but that is cubed. Okay, we want to get our units. So all we do is we cancel out 2 of those, and we cancel out 2 of those. So we're left with 2 kPas. So that then simplifies to kPa. Okay, like that. And it's like timesing it by -1 to bring it up. So your final unit is going to be kPa to the minus 2. So your full answer is going to be 5.29 times 10 to the minus 3, with the units being kPa to the minus 2. In our next question, we want to calculate what the partial pressure of nitrogen is in a gas mixture, and we don't know what the rest of the gas mixture is, containing 78% nitrogen by volume. A really important thing is by volume. So basically, when it comes to things that are the same temperature and pressure as each other, and this is a mixture of a gas that are all in the same place, so it'll have the same temperature and pressure, whatever that temperature and pressure is, we can see the pressure is there. Okay, that means that the same volume will have the same number of moles. So if I have 1 decimeter of this mixture, okay, that 1 decimeter of another mixture of another gas will have exactly the same number of moles. So if I had 1 decimeter of nitrogen and then 1 decimeter of oxygen, same number of moles in each because they're the same temperature and pressure. Now if that is the case, if I know that it's 78% by volume, I know that 78% of this volume is nitrogen. That means that in terms of the mole fraction, okay, that means 78% of the mixture by moles is nitrogen. So let's put that to the side. And so all we actually need with this question is this. It's 78%, we convert that to 0.78 and we times it by the total pressure, because that's like the mole fraction, because essentially same temperature and pressure of a gas will be the same number of moles. And you get your final answer of 7.8 times 10 to the 4 pascals. So our next question wants you to find the partial pressure of one of the components by giving you the number of moles of each part of the mixture and the total pressure. Now this one looks a lot more complicated than what it is. So you know that the mole fraction for this, if you do a quick mole fraction calculation, let's put this to the side. Okay, so a quick mole fraction calculation, 1.2 plus 1.8 plus finishing off our 1 mole, okay, is equal to 4 moles in total. Okay, so we've got 4 moles in total. That means our SO3 is going to be 1 divided by 4, okay, which is number of moles of the SO3, and then the total moles, which is 4, which I'm going to leave like that because it's a nice handy quarter. Okay, so that means if we take 200, we can convert that quarter into a number and just say 0.25. Okay, so our mole so this is going to be equal to our mole fraction. That's our mole fraction, and that's going to be our mole fraction of our SO3. So we've done a mole fraction of SO3, and then we know that our partial pressure, so partial pressure of SO3 is going to be equal to our mole fraction, which is 0.25, times our total pressure. And our total pressure down there is 200 atmospheres. Okay, so 200 atmospheres, which gives you a final answer of partial pressure of SO3 is 50 atmospheres, again using the same units that we had before, and that is how you work out the partial pressure of a single component when you have the moles of the individual components, okay, and you have the total pressure. In this question, which is one of the most difficult ones to understand, we've got this equilibrium here done at 2 different temperatures, and then we've got the Kp values for those different temperatures. Notice the Kp values have changed because temperature changes the value of Kp. Now if you look here, predict the reason why or whether the forward reaction is exo or endo, we'll go through that first. Okay, and then the pressure increased at the same temperature, state and explain. Okay, so this state and explain is really important. So we're going to go through that first of all. Okay, predict with a reason whether it's forward reaction is exothermic or endothermic. Well, first thing that says, again with the state and explain that's in the second question as well, you've got to say 2 different things. Now this is only worth 1 mark, but you still got to say 2 different things, and that's how it gets more difficult. So if you're going to predict with a reason, you've got to use the data. So if you look here, the data we've been given is up in this table. But always read the beginning of the question. Predict with a reason, state and explain, describe and explain. They all mean the same thing, okay? It means you must explain your conclusion using data given, okay, and make a conclusion. Now, that means from there, I've got to use temperature and I've got to use the Kp values. All right, we will do in a second. And it's a 2-part answer, even if it's only worth 1 mark. So a lot of times you think there's 1 mark here, I only need to say 1 thing. No, I'm sorry, you need to say 2 things. If they say predict with a reason, state and explain, describe and explain, you've got to say 2 things. And we know here, first of all, one of the things we've got to do is this temperature and this Kp value. So if we look at the temperature and Kp value, and we'll come back to this Kp equation in a minute, you can see that the temperature has increased. And then if we look here, you can see the number has got smaller. So our first statement is going to be that that the temperature has gone up, but Kp has gone down. Then it says whether it's exothermic or endothermic. So you notice here, that means that if the Kp has gone down, so the Kp has gone down, that means this numerator must have reduced because it's this number that's gone down. So this number must have got smaller. And if that one gets smaller, this one gets larger. So the equilibrium is to the left, okay? So like I said, that's going to get larger. Now, if that is the case, that means your yield's going to go down because the amount of this stuff that you make, this stuff here, it's got to have gone down. The number's gone down, and therefore the amount has gone down. Remember, pressure is related to concentration, so the amount that you make has got to go down. Now, that means if I'm going to increase the temperature and basically the amount of product is going to go down, then it must be following the backward arrow. So you see it here, very small here, but the backward arrow is at the top going that direction, which means that it must be following the endothermic direction. So as I increase the temperature, it's going to do the opposite. It's going to follow the endothermic reaction, and if that means the yield of the product is going down, the endothermic reaction must be going backwards. That means if it's endothermic in the backward direction, then it's going to be exothermic in the forward direction. That is all the understanding that we're talking about, but let's now talk about what you actually write for the question. It's really important you understand this. It's exothermic because when the temperature increases, Kp decreases. So all of that thinking is not really necessary for the question. You've just got to say that it's exothermic and then use the data in the table, and you'll get your full answer. So now we're going to state and explain in terms of Kp. So that's really important. State and in terms of Kp, what happens when the pressure is increased. So we've tried to do it in a general way first before we attack the question. Imagine there is 2 moles of N2, and they're represented by these 2 balls here. So they're the 2 moles. And then there's 1 mole of O2. So you see it here in yellow. So in total, we have 3 moles. Imagine the N2O is the blue balls, and you've got 2 moles there. Now imagine if the equilibrium was all the way over to the right and we just had N2O, then we would have 2 moles. And if we just had the reactants, we would have 3 relatively to each other. Now that means if we were all the way over to the right, we would have a lower pressure, and we were all over to the left, we have a higher pressure. So here would be a higher pressure than the lower pressure on the right. So if we want to lower the pressure, we need to go towards the products, and if we want to increase the pressure, we need to go towards the reactants. Now, in the question it says pressure is increased and the temperature is maintained the same. So we're going to increase the pressure of this by just reducing the size of the container. Now starting off, that would be 3 moles per decimeter cubed and then 2 moles per decimeter cubed because of the number of moles we've got represented here. So if we reduce the size of the container, you can see that goes up to 6 and that goes up to 4. So we've got an increase from 3 to 6 and 2 to 4. And that means 3 to 6 is a larger increase. So that means as soon as we apply that higher pressure, we're going to see an increase in the concentration of the reactants higher than the increase in the concentration of the products. So that large increase in reactant concentration means the equilibrium will then shift to the right to lower that concentration of the reactant. So all constants must stay the same unless the temperature is changed. So if a change is applied, the constant must be restored to its original value, because we only care about the constants changing in terms of temperature, and the temperature has not changed. So it's really important. So we need to describe in terms of Kp how it is changed back to its original, because it definitely changes at the start. So the first bit is this. So like I said, the general term is that large increase in reactant concentration, and it goes to the right. Now the Kp expression is your concentration of reactants increases. So we already said that, large increase. And that would be your first of 2 or 3 marks. And it increases by a higher amount than the products. Now that means the denominator, which is the reactants, okay, which is the bottom, okay, of the Kp expression increases by more than the top. That means Kp originally will change. So originally changes. What happens then is that the Kp needs to be restored. So it shifts to the right to increase the concentration of the products, which is the numerator. So notice I've used the word denominator and numerator because you can use those in your expression. So right at the start, you see Kp changes, and then afterwards the equilibrium expression then restores the Kp to the same value as it was before by shifting to the right in this case. And you can do it the opposite as well. For example, if there was a lower pressure increased, you'll see the opposite of this. Okay, and this is quite a common question. And remember, if they say state and explain in terms of Kp, then you've got to go through these different points. Explain what happens to Kp first and why it happens, and then explain how it gets restored to its original value. In this video, we've gone over all the types of exam style questions that you might get in relation to Kp. Now is the chance for you to test your skills by either doing the worksheets that are attached to this video or challenge yourself to go on to do the practice exam on equilibrium, which comes up next.